It's not working.
So it's a kind of matrix.
Do you think it's loading? Oh yeah, that's wonderful. I'm sorry, I should have answered all the questions before I open this thing here. So the thing on the left is the shuffle algebra I had in the beginning of this talk. The thing on the right is the new one.
Argo spectral parameter doesn't satisfy the inverse equation that you wrote.
Well, you have to put in the spectral parameter into the Young-Baxter equation. Yep. Well, to save on time. So here's how.
Well, I mean, that it satisfies the version.
Yeah, of course, but everything was set up with spectral.
Okay, so the thing on the left is the old shuffle algebra, the one where S was a particular sub-vector space of rational functions, and the shuffle product is defined with respect to this expression over here. It's a symmetrization, and here you put a certain rational function which I had on the board before, and recall that this construction on the left gave you half of the quantum toroidal algebra in Greenfeld's presentation. The expression over here is the new kind of shuffle algebra. So first of all, because V is not just a finite dimensional vector space because it loops into a vector space, the algebra K plus will not be endomorphisms of V to the power K. It's going to be endomorphisms of V to the power K rational functions in Z1 through Zk. So that is, by definition, the substitute of the endomorphisms of Vk to the current setting. But the most important thing is an analog of this construction over here. The point is, if you take arbitrary rational functions on this side, the corresponding algebra will be too big. So instead, you look only at those rational function valued tensors. So these are endomorphisms of Cn to the power k whose matrix coefficients are rational functions in Z1 through Zk, such that these rational functions only have simple poles at these expressions over here. So Zi minus Zj q bar squared. It should actually say Zi is equal to Zj q bar squared, such that you have a condition on the residue of these poles. The condition is displayed in this picture over here. So I first have to explain what kind of residue we're taking, and then I will explain what does this picture mean. The residue we're taking is when we break up the set of variables Z1 through Zk into a disjoint set of chunks of cardinality K1, K2, ... Ku, and we take the iterated residue where the variables in each chunk are specialized to a geometric progression of ratio q bar squared. So for example, in this example, you take the composition 4 plus 3 is equal to 7, and you break up a group of 7 variables to a group of 4 variables that are set equal to y1, y1 q bar squared, y1 q bar fourth, and y1 q bar sixth, and the other group of variables are specialized to y2, y2 q bar squared, and y2 to the q bar fourth. Now I'm showing you over here a picture, and the question is how to think of this picture as an endomorphism of v to the power k rational functions in z1 through zk. The explanation is over here. So a braid on k strands, for example, over here you have a braid on 7 strands. It represents an endomorphism of Cn to the power 7 rational functions in Z1 through Z7. The concatenation of braids left to right corresponds to composition of endomorphisms in Cn to the power k, and the elementary endomorphism correspond to a single crossing, and the endomorphism which corresponds to a single crossing of strands with variables Zi and Zj is the R-matrix on the I and J on the ith and j factor with the spectral parameter Zi over Zj. And moreover, when you see this funny thing with the black bullet, I guess it corresponds to a permutation endomorphism. So when you see this kind of picture, and this is the ith strand, and this is jth strand, it corresponds to the permutation operator of the I and j factors. So with that in mind, the expression over here is a particular endomorphism of c squared to the power 7. And the condition says that the residue of x at this particular specialization should be some arbitrary thing on the first and the fifth copies of 7 copies of Cn, and then you multiply them on the left with a bunch of crossings which mean R matrices, and you multiply them on the right with a bunch of crossings which mean R matrices, and a bunch of these points which mean some permutations. So that is the condition. As a vector space, K plus is the subvector space of endomorphisms satisfying these conditions on the residues.
This sounds like a very complicated thing to prove.
Well, everything is easy after you do it. So right now it's an easy thing to prove, but a few months ago it was a complicated thing to prove.
And now, once again, there is no connection between Q and Q bar, right?
No, they
Completely
are different independent formal parameters. So Q appears in the R matrix, and Q bar appears in this funny residue condition, and it also appears in shifting the variable in this R tilde. Okay, and finally, I should remind you that the formula for the shuffled product of A and B can be represented as a braid in this way. So this picture over here is exactly what I had in formula as before. I had the symmetrization of a bunch of R's, then A, a bunch of R tildes, and then B. In terms of braids, it's exactly represented by this braid here, which arguably looks a lot nicer than what I had before. So the shuffled product in this algebra can also be represented as braids.
So this Q bar, is it like T in McDonald theory?
Yes, it's like T in McDonald theory, and I think it's also like the extra parameter which you have with Kajdan in your old paper on the on compositions of vertex operators. That's another story, and I won't have time to go into it. But it's connected with that kind of reflection equation.
But if you're gonna do the same for kind of double loops into some other not the A algebra.
Okay,
then
in
you're
some
gonna
G.
get instead of you don't.
You have to choose a representation first, and if that representation should probably be faithful. But if it's too big, then the algebra you will get out of this construction will probably be bigger than the quantum toroidal of that type.
No, what I'm saying in terms of the number of parameters.
Looks like Q bar, you have Q bar because
There's a cycle.
Right, I mean, it appears over here as the choice that you make in this R tilde. I mean, I guess if you take an...
No, also in your this comes into just if you wanna can geometrically construct this kind of whatever something corresponding to a curve or fine type, you only get an extra variable.
Oh yeah, sure.
If it's a type of A.
Sure.
Is that also the same?
I have not actually thought about the analog of this in other types, so I'm not sure what would appear. But right now it's only the matter of speculation that if you do this in other types, you will be able to get something that looks like G hat hat, but I'm not sure. I have not worked anything out. So I'm not sure what the analog of a parameter Q bar would be in other types.
This EI is the same as EI prime? Or
EI? I'm sorry?
bottom left? Is the EI prime?
I'm not sure I see EI and DI prime.
G,
So EI is for it. What D is for F is what E is for.
Oh, over here, yes. So D is for F, it's the number of variables of F. E is for G, it's like the number of variables of G.
But in the formula for G of dot dot dot,
Yes.
Is the EI the same as the DI prime?
Oh yeah, EI is DI prime. I'm sorry, that's a typo. So EI should be DI prime in this formula.
But quantum toroidal algebra for a fine type A has one more parameter than.
So that would be Q bar.
That's
Right, so that's why. So for other types, wouldn't this mean that you will not have this parameter?
I don't know exactly. So that's exactly what they asked.
Oh, yeah.
So it's only speculation now because I haven't worked any of this out in other types, and I'm not even sure if it works. in principle, some of the ideas should carry through, but I'm not sure. So I have a couple more minutes. Let me just state the main result over here. So with this choice of A, R, and R tilde, the theorem is that there exists an isomorphism between A, which is defined as the algebra generated by K plus, recall A minus. So this was a double algebra. It had a copy of A plus and a copy of A K minus for the same choice of R, but a slightly different choice of R tilde. And then you also had these extended generators, which were called Sij, Tij, but there are two copies of these, so one for the pluses and one for the minuses. So this is what the algebra A is. So you had all of these things modulo some relations, which I mentioned them in the case of a finite dimensional vector space V, and there's an analog in this setting. There is an isomorphism between this thing and the quantum toroidal we care about. So this is GLN hat hat. And here's how the Sijs and Tijs behave. So the Sijs and Tijs, if you recall the commutation relations in between them, these generate precisely a copy of UQ GL hat, GLN hat. So this copy of UQ GLN hat under this isomorphism is precisely what people call the horizontal subalgebra of quantum toroidal. K plus and A minus would be what lies above the horizontal subalgebra and what lies below. So if you want this this isomorphism to be made explicit, beside the fact that these Sijs, Tijs will go to the horizontal copy of the subalgebra inside the quantum toroidal, you need one more piece of information, and this piece of information is the fact that phi sends the element EII plus minus. So this is going to be has a matrix in one component and one variable. These are elements of A plus minus. They will go to with the following Cartan elements of the quantum toroidal, phi I to the plus minus 1. And I claim that if you have this assignment over here and the fact that the Sijs and Tijs go to the horizontal copy of GLN hat inside GLN hat hat, this completely determines an algebra isomorphism. The statement of a theorem is that this algebra isomorphism is well defined, and moreover, the coproduct that we have on this algebra by analogy with what we had in the finite dimensional case will give you a coproduct here, and moreover, quantum toroid over here will be the double of its half with respect to this new coproduct. So well, chi and j actually have to run not just between 1 and n. I should say that chi and j run over all pairs of integers, modulo conjugate simultaneous translation by n. So this is what I have. Thank you so much. Ooh. So you mean functions with no poles? Yes, but if you take the shuffle product of two polynomials, it will have poles.
Yeah, but if you have subalgebra generated by
the subalgebra, which is generated by the zi1 to the power k, actually coincides with s plus.
Yes.
And in the same way on this side, the subalgebra, which is generated by k is equal to 1 command will generate a plus. So that's a theorem. So
in principle, you don't need this condition. You can say that you have shuffle product and you move subalgebra.
Yeah, that's equivalent.
Huh? That's much better because if you say algebra generated by,
it's hard to get a hand on it.
I know.
So that's what.
But it's the same thing.
In this case, it's the same thing. In general, it may not be. I mean, it's saying that if you flip a crossing, you multiply everything with a scalar valued function. So in this case, in this kind of setting, a scalar f is not exactly a scalar; it's a scalar valued function, namely f of z1 over z2 is z1q minus z2 over q, z1 divided by q minus z2q, divided by z1 minus z2 squared. So that's a scalar valued rational function.
So this is the C where the kind of vertical subalgebra is.
It's not easy, but I do have formulas. So phi I1 it corresponds to a single EII. If you want phi ik is going to correspond to a particular rational function valued endomorphism of Cn to the tensor power k. And I can say what it is. I can give you a formula, but you know what to do with it is a different story. But it's possible to say something. Yep.
Are there representations and bases thereof that these shuffle elements act nicely with?
I haven't thought about the representation theory in general. What I can say is that this incarnation of the top half of quantum toroidal allows you to construct an evaluation homomorphism from GLN hat to the completion of GLN hat. And that is going to be given in terms of certain, say, vertex operators for Vermas of GLN hat, if you will. And these kinds of objects have been studied, I think, in the papers of Pasha and Kajdan, and they've actually been studied for 20 years. So the point of the shuffle algebra is, in a certain sense, is the algebra which encodes the composition of these kind of vertex operators.
So you think that will be an example of quantum vertex algebra or something?
Yeah, I mean, at least an example. I'm not sure if I can get more meaningful examples other than affine types, but I think that that's what it is.
Well, since you brought it up, maybe I can ask this question. But I want to take, I want to produce the R matrix for the double for GLN hat in terms of just the R matrix for GLN hat. And one way to do it is take some kind of infinite product.
Yeah, that's right.
And that's is that point of view at all aligned with what you do here, or is it just what you're talking about?
To be honest, I'm not really sure if this helps. You could get something. For example, you could say that if you think of universal R matrix as some kind of canonical tensor, it's going to be a sum over all k of the canonical tensor.
No, I meant something.
Well,
I meant something different. I meant.
Oh, if you actually want a product over roots.
If I take a Duncan diagram, I can unfold it to a infinity.
Yes. Oh.
So if you take like you have a infinity R matrix, and but then you multiply it with that shape with itself, you're getting the R matrix for the.
I haven't thought about actually computing it, proving it in this way. This seems to me to be a statement about the R matrix of GLN hat.
This, well,
or something.
you do it with the spectral parameter, that would be going from the R matrix for GLN hat to the R matrix for GL infinity kind of hat to GLN
And hat. I haven't thought about writing it in this way. So with this kind of shuffle algebras, and this appears already in the paper of Mudrov, there is a canonical way to write down its universal R matrix, but I'm not sure it converges in any kind of meaningful way in representations we care about. So I'm not sure if this presentation tells you anything about that. But your idea is different. I mean, that's a different direction.
Other questions?
Thank you very much.
We'll be back at 4:30. Last stop.
Sorry.
Yes. Essentially, I have one. So this 45